I think. Okay. So students, can I, the point about the photoelectric effect is, it is given a stepmotherly treatment in our textbooks on modern physics, our textbooks on general physics, our textbooks on various concepts of physics, our coaching class books. And it is, I would believe, a grave injustice to this very, very subtle and important phenomenon. Okay. So let me describe it. I have a presentation for it. Can I share the screen right now, Praveen? Good.
Yes,
I'm allowed to share it. Thank you. Thank you, Yogita. Okay. Here is the photoelectric effect. If you have any questions, here is my email ID, physicssutra@gmail.com. And this particular talk will also be there on a channel called Physics Blank Sutra Blank Official. It's called Physics Blank Sutra Blank Official by tomorrow, I think, even tonight. So the photoelectric effect, and I am trying to share Einstein's perspective on it. Okay. As I said, it is given a stepmotherly treatment in our textbooks. So we get the sanitized view. The textbooks at high school level or undergraduate level, and even teachers, describe the effect as a single equation of energy conservation. Then they may pay some lip service to the notion of the photon. There is something called photon. Photon has energy HF. Okay. And then they say move on to other interesting topics in physics. In fact, I find it very painful when I'm describing this effect to students. If they say, no, we know the photoelectric effect. We know the effect. Now, can you tell us about the uncertainty principle? But this is a sanitized view and does little justice to Einstein's enormous intellectual struggle with this phenomenon. By the way, Einstein did not coin the term photon. Is my presentation clear, Yogita?
yes, sir, it's clear.
Thank you. So in 2005, the United Nations decided to celebrate it as the World Year of Physics, mainly because in that year, 100 years ago, okay, that's the centenary of three famous papers by Einstein. One on the photoelectric effect. It was called On a Heuristic Point of View About the Generation and Transformation of Light, okay, 1905. The other one was on the electrodynamics of moving bodies, that is special relativity. And the third one was on Brownian motion. Out of these three effects, okay, this is what Einstein thought that this paper was the most significant, not the special theory of relativity. Okay. It might also interest you to know that the paper which has been referenced the most since that time of the three papers by Einstein is the one on Brownian motion, because it is used also in economics. So what was the photoelectric effect? Einstein writes to his friend Konrad Abicht, I promise you 4 papers, the first of which I would send you soon. Okay. And Einstein, and here's the photoelectric effect. Basically, you shine light on a metal ball, you'll get electrons out. It was the subject of intense study by physicists Hertz, Hallwachs, Thomson, and most importantly by Leonard. Okay. And Leonard's 1902 paper provided some insights to Einstein in his work. The photoelectric setup is very simple. We all know about it in the abstract. I mean, it's actually quite complicated. Okay, you shine light on a cathode and you have an anode at a positive potential. Electrons which are released would go towards the anode and you would register a current. Normally, you do the opposite also. You actually make this anode negative so that electrons just stop. That's called a stopping potential. So if the stopping potential is Vs or larger than Vs, there will be no current. Okay. Now the schematic view hides many things. It hides things such as that the tube should have very low pressure. It's a very low pressure tube. Okay. It hides the fact that these electrons should be such that they do not interact significantly with each other via electromagnetic or electrostatic interaction, and many other things. Okay. So this effect, the photoelectric effect, is captured in a couple of experiments. It's captured by this one experiment on the intensity of the light. Okay. And this was one of the puzzles. If the voltage is positive and the intensity is low, this is called the saturation current. The saturation current is low. If the intensity of light is high, then the saturation current is high. However, the stopping potential, which is right over on the negative side, is the same given the metal. It does not change. So you can have a very strong intensity light, a 2000 watt bulb, or you can have a 10 watt bulb, but the stopping potential will remain the same. What will change is the saturation current. This, since I'm dealing with the students and with an audience which is very, how should I say, very talented and they are well read, this is well known. What is also well known is the second effect. Okay, and that effect, let me try to explain it. Okay, if you have a 100 watt light source, a UV source, and you shine it on a metal. Okay, so if it's say at 2 meters, if the bulb is at 2 meters if the bulb is at 2 meters from the metal, the intensity at the metal would be 2 watts per meter square. Now you look at a blow up of a single atom, okay, and see how much energy falls on this atom. Okay, supposing the atom has an area of 10 to the minus 19 meters square. Okay. That is because an atom is the size of 1 angstrom. So you take pi r square, so 10 to the minus 20 into pi, say it's 10 to the minus 19 meters square. Then the energy soaked up by a metal atom is approximately 2 into 10 to the minus 19 joules per second. That works out about 1 electron volt per second. Now, usually, the work function of the metal is about 1 eV, 3 eV, 4 eV. So it will take a second or two for the electron to soak up the energy of light and leave the atom. Okay. This is called the evaporation model or the soaking up model. You soak energy in and then the electron leaves. The electron takes some finite time. It takes about 2 seconds, 3 seconds to leave. However, it was known even to Leonard, and Leonard puzzled over it. The photoelectric effect is instantaneous. In those days, at 1902, it was as instantaneous as 10 to the minus 6 seconds or less than a microsecond. That was the puzzle. And how is this happening? Okay. So what Einstein says, he gives due credit to Leonard, and I think in this talk I will stress mainly what Einstein himself has to say in the paper. The usual conception that the energy of light is continuously distributed over the space through which it propagates encounters serious difficulties when one attempts to explain the photoelectric phenomenon, as has been pointed by Leonard in his pioneering paper. So this point Einstein recognizes, okay, and credits Leonard for it. What I have on top over here is the various phenomena that can be explained using the corpuscular view or the wave view. Okay. If there's a corpuscular view, you can explain reflection and refraction. With the wave view, you can explain all of these: reflection, refraction, interference, diffraction, and polarization, but cannot explain the photoelectric effect. Okay. So let me continue. Okay. So here is a conception of an artist's conception of traveling light. It is not a wave. It is basically a packet of energy. And let me once again quote Einstein. This is the last but one paragraph by this great man, the great physicist and the great thinker. The energy of a light ray is not continuously distributed over an increasing space, but consists of a finite number of energy quanta, which are localized at points in space. Okay. And look what he says, which move without dividing and which can only be produced and absorbed as complete units. So this is how he describes the photon. I think it's a wonderful derivation, and I've memorized this description of the photon. They're localized in space, move without dividing, and can only be produced and absorbed as complete units. Okay. So it's almost like this. I was thinking how to explain it to a high school student who was in 9th standard. And I told him the following analogy, and that is, you're in a mango orchard in the summer and there's a mild breeze. Does the mango fall? Not often, but perhaps once in a while. If, on the other hand, you pick up a small stone and aim it at a twig holding a mango, the mango will fall immediately. Okay. So that is the analogy. Or that's the analogy for, say, if you're trying to describe it to an 8th or a 9th standard child. Okay. And this tight bundle of energy is what Einstein called the light quanta. Okay. So a continuous flow of light will not dislodge an electron instantaneously from a metal atom, but a bundle of light would. Okay. And this is just another analogy for the photoelectric equation. You draw energy from a well. You have to, mgh is like the work function. You throw the water out from the well. It is like the kinetic energy of the electrons. So instead of E, you have h nu. Instead of mgh, you have phi, which is the work function. And here is the kinetic energy of the electron. So this is another analogy. And this is for a small child, say in 8th or 9th standard. Not for you, but for you. For you, there's something else. Okay. So this is the photoelectric equation of Einstein, where the energy of the light has to be greater than all of this. Okay. The kinetic energy and phi. Okay. Phi is the work function. And here is a picture of it. Okay. There's a work function, which is the potential energy in the well, the kinetic energy of the electron, and the energy of the light. Okay. And what you find here is a quote from that paper. Okay, you might find all of this a little foreign, okay. But and the whole how should I say, the dictionary has to change. Okay, what he means by this phi is basically the stopping potential, and what he means by E is the charge of the electron. But he's talking in terms of Avogadro number. So this E is equal to the Avogadro number into the charge of the electron. Okay. This is the stopping potential. This P prime is basically the analog of the work function. And what you see over here is the energy of light, photon, so to say. Okay, R is the same as the gas constant. Beta, unfortunately, is not 1 by kT. Okay, beta is the Planck's constant divided by the Boltzmann constant. Planck. So if you do that, you will get h times nu. Okay. This is from section 8 of Einstein's paper, the last section of the paper. And this equation which Einstein proposed, which is what is the photoelectric equation now used in textbooks in a sanitized form. Over here, I've told you what it is in modern parlance. You should listen to what Millikan has to say in 1916. Einstein's photoelectric equation appears in every case to predict exactly the observed results. I mean, this equation holds very well, he says. The photoelectric equation holds very well, okay? Yet, the semi-corpuscular theory by which Einstein arrived at the result is wholly untenable. I mean, it's such nonsense, he said, that, I don't want to believe it. So the question is not that you have an equation which agrees with the experiment. The question is the physical picture behind it is not something which I can swallow. That is what Robert Millikan is trying to say. Millikan is the same person as that of the electron charge, Nobel Prize for the charge of the electron. Okay. And this is another experimental proof. I think most students have seen this. If you look at the maximum kinetic energy and plot it as a function of frequency, The slope will give you something very close to that of, I think it will give you the Planck's constant divided by the electron charge. And these are different threshold frequencies for different metals 1 and 2. Okay. So very good. I mean, the point is not that you have a successful equation, which it is. Admittedly, this equation works very well and has been captured in all our textbooks. But the point is even more fundamental, is how did Einstein justify the light quanta concept? How do you justify this concept? So let me quote again from Einstein, again to Konrad Habicht, and see what he says. I promise you 4 papers, the first of which deals with radiation and the energetic properties of light and is very revolutionary. Notice, he does not call the special relativity paper as revolutionary. There's only one which is revolutionary for him, and it is this paper. The paper contains a preamble and 9 sections. And I can share the paper with you also, but you can also download it. Please do it, I would say. One section, approximately 10%, deals with the photoelectric equation. I should not say effect, but equation. 6 sections, 60% of the paper, sections 1 to 6, are devoted to justifying the notion of the light quanta. Okay. So this is what the essence of the paper is. The essence of the paper is not the photoelectric equation, but it is justifying this concept. He calls it Licht-Quanten. Okay. And to do that, you have to understand what Praveen's talk, okay, and what Dr. Praveen Pathak did. He started with the entropy of the ideal gas. Okay. And if you forget the temperature part of it, the entropy is given by K log omega, the very famous formula that is there on Boltzmann's grave in Vienna. Okay. And this omega, supposing you have n particles, n gas particles in a volume V naught, and you ask this hypothetical question, what is the probability of finding all the n particles in a smaller volume V? Okay. So that probability of finding n particles in a smaller volume V is V by V naught to the power n. Okay. And therefore, if you were to write the difference in entropy, it is K log V by V0 to the power n. This is perhaps a poor man's way of deriving this equation. There are more rigorous, and I'm sure Praveen has gone over it with you. The entropy of an ideal gas as log V by V naught plus another log T by T naught, which we ignore for the moment. Okay. So actually Einstein quotes this formula, by the way. He knew, I mean, he didn't invent this formula, but he quotes it. Okay, here it is. So that I can convince you, this is section 5 of 1905 paper. It is V by V naught to the power n. And the difference in entropy is simply log V by V naught. I think there's a small printing mistake, and there's some quantities over here. There's an n, of course, R is the gas constant. Okay. Okay. Am I clearly audible?
You are, sir. You are audible.
Okay, thank you. And this thing is visible, no? Yogita? Okay.
Yeah, it's visible, sir.
Okay. If something goes wrong, give me a call.
Sure.
And once again, thank you, Yogita. You are plotting the energy density of Rayleigh jeans, the experimental points of the 4 German physicists, experimentalists, and this is the Wien distribution. So what Einstein did was he decided to work to justify the light quanta. He took light as black body light, okay, and tried to derive the entropy of the black body radiation. Okay. Now the entropy of the black body radiation can be derived, but were you to use the Planck formula, okay, the calculation is very difficult. So once again, you go back to the Wien's formula to calculate the entropy of the black body radiation. So you might wonder why I stress the Wien distribution so much, because it keeps recurring again and again. in a very recent paper that I worked on how should I say, the efficiency of solar cells, I once again used the Wien distribution, okay, because it's easy to work with. Okay. And I remind you what is the formula for the Wien distribution. There's a nu cube by c cube. This is all that you have to remember. And there's an e raised to minus h nu by kt. Okay. And let me quote Max Planck now in his Nobel Prize acceptance speech. Even if the radiation formula proved to be perfectly correct, it would, after all, have been an extrapolation, I said an interpolation formula, found by guesswork. He's talking about his own work. And after some weeks of the most intense work of my life, and this is with thermodynamics, light began to appear to me. I've made a mistake here, appear to me, and unexpected views revealed themselves in the distance. So this is how the great Max Planck talks about his work. He said, my Planck formula is correct, okay, and it has the right interpolation between Wien and Rayleigh genes. But interpolation is not sufficient. I have to justify this formula. And it took him several months, he says few weeks, but I think 2 or 3 months of very intense work and thinking to derive this formula. It is the same with Einstein regarding the photoelectric effect. The equation is there as an energy conservation equation. How do you justify this? Okay. So, once again from the great man's paper, section 1 and 2, if you look at the Rayleigh genes formula and you integrate it over all frequency, you get an infinity. Okay. I'm showing this all this to you because I'm trying to tell you how Einstein is struggling with this concept of the light quanta. And this is from section 6 of the paper. And I don't know if I can blow it up. This is the formula I asked you to derive. And a couple of very enterprising students did it. And they got an answer 3RT, okay, or 3KT. Okay. And I would urge you to read this part to see the significance of this number, of this formula, or of this derivation. Okay, there's the same derivation in section 6 of Einstein's paper. So you look for the entropy of the radiation given by the Wien's formula. So the energy is V times the radiation density. It is right here. I remind you once again, it is nu cube e raised to minus h nu. Let us call all of this as C1 and simply take the exponential part, which is the dominant part. Okay. And take the log of both sides. For you to take the log of both sides, you'll get 1 over temperature. You'll get a log over V, you'll get a log over E. Okay. And then you have to recognize that 1 over T is nothing but derivative of entropy with respect to the energy, something I think that Praveen alluded to at the end of his 2 talks or 3 talks. Okay. And all that you have to do then is to do an integration. So ds is equal to d into all of this, integrate, and the only integral which is probably a little challenging for us is the integral of log e dE, which is e log e dE. So here it is, the integral of that integral. That integral of log x, x log x minus x. Okay, that is what he did. So the entropy then turns out to have this form. Okay, and now you're home because you just focus on the first term. This is the volume. You focus on the term Ke by h nu. Okay. And you basically have the entropy is equal to log V Ke by h nu. That's to the power this. I'm writing it right here. So basically you have the entropy is the Boltzmann's constant, log of the volume raised to E by h nu. Okay. Okay. Now, if there are n photons or n light quanta, E is equal to n times h nu, he said. Okay. And therefore, you get a consonance with the ideal gas formula. So using this study of the entropy of the black body radiation with the Wien formula, Einstein justified the fact the energy of a photon is h times nu. And this is his line of argument. Okay. So And I once again flashed his paper. There's a section 4 of the paper where entropy is once again, here is the formula, E by beta nu log V by V naught. Remember, I told you beta is equal to H by K, okay, the Boltzmann's constant. Beta is not 1 by KT in this paper, okay. And he quotes Boltzmann over here, okay, and he credits Boltzmann with this formula. And I continue with this paper. So I would share this with you, of course. It will be available on the YouTube channel Physics Blank Sutra Blank Official by tomorrow. But let me continue with the story. Einstein never used the term photon. The chemist Gilbert Lewis coined it in 1926. In describing his triad of epoch-making papers, he characterized only one on the light quanta as truly revolutionary. And he got the Nobel Prize for it in 1921. There's a whole series of Nobel Prizes around this, one to Wien, Max Planck, Millikan, and I may have gotten this date year wrong, whether he got the Nobel Prize in 1918 or 1920, I'm not sure. Okay. And the photon concept, the fact that the entropy of light is of the form of n times h nu, okay, divided by h nu, is such a fertile idea that it has gotten a large number of Nobel Prizes, most notably to Compton for the photon momentum, and then, for example, to Mossbauer for recoilless emission. Okay, and when a photon is released, the atom has to recoil. So both of them, the Mossbauer effect and Compton effect, have to do with momentum conservation. And of course, Bose-Einstein statistics, for which Bose never got the Nobel Prize. It was given for the observation of Bose-Einstein condensation to physicists in the late 1990s. Okay. So what Einstein says is, I'm ceaselessly occupied with the problem of the constitution of radiation. He doesn't think that what he has shown is the proof. He says it's a heuristic argument. The question of quanta is so extraordinarily important and difficult that everyone should be concerned with it. This is what he says in a letter in 1909 to Jacob Lamb, not L-A-M-B, but L-A-M-P. Okay. And then he went on to investigate this to understand the specific heat of solids and energy fluctuations of the thermal radiation using the Planck distribution. There's also a very interesting paper of his in 1918, I believe, or 16, which foreshadows lasers. So basically, 6 sections to justifying the concept. Yeah, I can quote Tennyson, for example. I would like to quote Tennyson in this matter. He was struggling and he was caught between two worlds. Caught between two worlds, one dead, the other powerless to be born. Okay. And then there's a whole series of other papers. I think I mentioned 2 over here. There's one on momentum fluctuations, one on a letter he wrote to Michel Besso on lasers, so to say, and the one in which he extends Bose's derivation of Planck's law to predict Bose-Einstein condensation. A very fertile idea, but an idea that he claimed even till the end of his life that he didn't quite understand. Okay. And here is the last quote by this great man. All these 50 years of conscious brooding have brought me no closer to the question, what are light quanta? Of course, today, every knave or every fool thinks he knows the answer, but he is deluding himself. This is in a letter to Michel Angelo Besso in 1951. So I hope that by these 2 talks, I have convinced you that the study of black body radiation is important. The study of thermodynamics is very, very important. And I have to tell you that several of these physicists Wilhelm Wien, Max Planck, Albert Einstein, Paul Ehrenfest, Karathia Dori, and a whole host of these physicists in the early 19th, 20th century were past masters or were great students of thermodynamics and statistical mechanics. And let me quote by a end by let me quote Stephen Spender in this matter. It's a poem by him. It says that I think continually of those who were truly great. I think continually of those who were truly great, who in their lives fought for life. Born of the sun, they traveled a short while towards the sun and left the vivid air signed with their honor. So thank you for indulging me, and I should stop sharing, and I will be sharing this with you anyway. Okay, so I'm done. Yogita and Praveen, I'm done with this.
Thank you, sir. It's 10:40. We have 5 minutes. We can quickly take questions if students have any questions.
Okay, you can stop recording now.
Yes, sir.
Okay, so is there any question? I mean, any